In this course, we will learn about how to use psychrometric charts. Here, we will look at mixture of air. Air changes its state depending on changes in the temperature and mass of water vapor in the air. A psychrometric chart allows one to pinpoint the air under a certain condition and understand the properties of such air at a glance. It also allows for a display of how the state of the air alters, and, thus, a display of the air conditioning process. For example, this chart represents how the state of the air alters during cooling operation. Engineers often utilize the characteristics of the psychrometric chart to design and select air conditioners and plan air conditioning systems. Let's take a look at what we will be learning today. In order to create air with the temperature and humidity required for cooling and heating, air conditioners carry out various processes, including mixing, cooling, heating, dehumidifying, and humidifying of air. In this course, we will learn about the process of mixture of air among these processes. First, we'll review what composes the psychrometric chart. Then, we will use it to think about mixture of air. Let's now take a look at what composes the psychrometric chart. The horizontal axis represents the dry bulb temperature, and vertical axis the absolute humidity. The curve on the upper left is the saturation line. On the psychrometric chart, the state of the air is represented by one point within the area enclosed by these lines. From one point that represents the state of the air, you can read 7 properties of the air. These are the dry bulb temperature, wet bulb temperature, dew point temperature, absolute humidity, relative humidity, specific volume, and specific enthalpy. As long as 2 of these 7 properties are known, you can locate the one single point representing the state of the air on the chart. And this one point can tell you the 5 other properties. This illustration shows a typical air conditioning system in which an air conditioner is used. Some of the air discharged from the room is sent outdoors directly. The remaining air is returned to the air conditioner, and this air is called return air. In order to maintain clean room air, air is taken from outside and mixed with the return air. The mixed air is conditioned to an appropriate state and supplied to the room. Now, let's take a moment to think about this mixing of air. Let's assume that the air returned from the room to the air conditioner has a dry bulb temperature of 26 degrees Celsius, a relative humidity of 50%, and airflow of 1,000 cubic meters per minute. The fresh outdoor air taken in by the air conditioner has a dry bulb temperature of 33 degrees Celsius, relative humidity of 70%, and airflow of 200 cubic meters per minute. When these two are mixed, what will happen to the state of the air? Let's use the psychrometric chart to think about this. The air that returns from the room has a dry bulb temperature of 26 degrees Celsius and relative humidity of 50%. Let's call the point representing this air state point 1. The fresh air taken from outside has a dry bulb temperature of 33 degrees Celsius and relative humidity of 70%. Let's call the point representing this air state point 2. Now, connect state points 1 and 2 on the chart. Divide the line between state points 1 and 2 based on the ratio of the airflow of these two types of air, that is 200 to 1000, and call it state point 3. This is the point that represents the state of the mixed air. The dry bulb temperature, absolute humidity, and specific enthalpy for state point 3, representing the state of the mixed air, can be obtained with a proportional calculation using the respective values of state points 1 and 2. For example, the dry bulb temperature for state point 3 is calculated by adding 200s in 1200s of the temperature difference between state point 1 and 2 onto the temperature for state point 1. The absolute humidity can be calculated in the same manner. The same is also true for specific enthalpy. The state of the mixed air at state point 3 was obtained using the airflow represented by the volumes at state points 1 and 2. Now, let's determine the state point of the mixed air using the airflow converted to mass. The psychrometric chart shows the air's specific enthalpy and absolute humidity on a per kilogram of dry air basis. In order to understand the state point of the mixed air more precisely, it is necessary to calculate it using the airflow represented by mass. At state point 1, the specific volume is 0.835, so the airflow is calculated to be 1,198 kilograms per minute. At state point 2, the specific volume is 0.90, so the airflow is calculated to be 222 kilograms per minute. Therefore, you can locate state point 3 at the point dividing the line between state points 1 and 2 from state point 1, according to the air-mass ratio of 222 to 1,198. We calculated the state point of the mixed air in two ways. We used the volume ratio in the first calculation and the mass ratio in the second. Now, let's compare the property figures for these two state points of the mixed air calculated. The dry bulb temperature is calculated to be 27.2 degrees Celsius using the volume ratio. It is calculated to be 27.1 degrees Celsius when the mass ratio is used. The difference between these two figures is only 0.1 degrees Celsius. Let's compare the other figures. These are the wet bulb temperature figures. These are the relative humidity figures. These are the absolute humidity figures. These are the dew point temperature figures. These are the specific volume figures. And these are the specific enthalpy figures. As you can see, there are virtually no differences. Generally, we use the volume ratio to calculate the state point of the mixed air. Next, let's think a little more about the relationship between air volume and mass. This shows the typical movement of air during cooling. State point 1 represents the air that has returned to the air conditioner from the room. State point 2 represents the outdoor air. State point 3 represents the air where the air at state points 1 and 2 are mixed together. The mixed air is cooled and dehumidified by the cooling coil in the air conditioner and becomes the air at state point 4. The air distributed to the indoors absorbs the load in the room, becomes the air at state point 1, and returns to the air conditioner. In this manner, the specific volume of the air changes because the temperature and humidity differ at the various locations along the pathway by which the air is transported by the air conditioning system. The state of the air is continually changing. It would be inconvenient to calculate the air mass with every change. In order to make the calculations convenient, the air mass is generally handled assuming the actual air as the standard air. The standard air refers to air with an atmospheric pressure of 101.3 kilopascals, dry bulb temperature of 20 degrees Celsius, and relative humidity of 0%. The specific volume of the standard air is 0.83 cubic meters per kilogram of dry air. When comprehensively considering these air conditioning processes on the psychrometric chart, air is generally converted into the standard air with a volume of 0.83 cubic meters per kilogram, regardless of the state of the air. The following is a summary of what we have just learned. When combining A cubic meters per minute of air at state point 1 and B cubic meters per minute of air at state point 2, it becomes A plus B cubic meters per minute of mixed air at state point 3. This point is a point dividing the line between 1 and 2, according to the B to A ratio. This point also divides the dry bulb temperature, absolute humidity, and specific enthalpy differences between state points 1 and 2, according to the B to A ratio.